Hello, and welcome to today's webcast, brought to you by Industrial Laser Solutions, Laser Focus World, and Endeavor Business Media. Today's webcast, titled Materials Processing, Lasers, Optics, and Testing, is sponsored by MKS Ophir and MKS Spectrophysics. Today's event will be presented by Scott White, Director, OEM Product Marketing at MKS Spectrophysics, Jim Bovatsek, Applications Lab Manager at MKS Spectrophysics, and John McCauley, Business Development Manager at Ophir. After the presentation, we will host a live Q&A session. My name is John Lewis, and I'll be your moderator today. Before we begin, a few words about this webcast technology. This platform allows you to customize your webcast console to suit your own preferences. You can move windows around by dragging the title bar or resize your windows by clicking on the lower right corner of any window. We encourage you to ask questions at any time during the presentation by using the Ask a Question box in the presentation window. We'll be holding a Q&A session right after the presentation. Also, if you have any technical difficulties during the webinar, just type your issue into the Ask a Question box and a member of our team will assist you. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the Industrial Laser Solutions website. I'd like to note that a locked PDF of John McCauley's slides are available along with a few other resources in PDF format for your download today. It can also be downloaded during the on-demand version of this webcast by clicking on the Event Resources tab just under the Ask a Question box. Now it gives me great pleasure to introduce our first speaker, Scott White. Welcome, Scott.
Thank you very much, John. Thank you, John. Appreciate it. My name is Scott White, Director of OEM Sales at Spectra-Physics. In our first presentation today, we'll be discussing glass cutting and micro-welding with industrial ultra-short pulse lasers. I'd like to, first of all, thank the folks at Laser Focus World for hosting this webinar, and we look forward to sharing our information with you. In the first part of the presentation, I'll talk just a little bit about the background of the company and our emphasis, and then go into some of the specifics of the lasers used, and then we'll start talking about results with my colleague, Jim Bovatsek. So first, just a little bit about MKS. We are a sizable company, over $2.3 billion in annual sales and 5,800 employees, and we focus and work very hard on being a market leader in several industrial sectors, specifically semiconductor, industrial technologies, life and health sciences, and research and defense. We also work very hard at providing innovative solutions to solve our customers' complex problems. And this can range in technologies from vacuum processing to, of course, laser solutions, motion and photonics and optics, and laser-based equipment. So we look forward to sharing with you some of those solutions today. In the light and motion division of MKS, we have a phrase that we call surround the workpiece. And what this means is that we are providing, of course, the laser light sources to process various different types of materials. We also provide the various beam delivery equipment to deliver that laser light to the workpiece in the fashion that the customer is looking for, the motion system to control the workpiece underneath the laser beam, and then finally, of course, all of the process control equipment, which my colleague John McCauley will talk about in the second presentation. Specifically, at Spectra-Physics, we consider ourselves to have differentiated core technology in the field of lasers and industrial lasers specifically. And it starts with our proprietary optical coatings, which we have made significant advances with in recent years to develop not just ultra-short pulse lasers, but also UV and green laser technology. We have some advanced electronics and controls that are used to create different kinds of pulse waveforms with the lasers which can enable different processes and, in fact, in some cases, can actually increase the speed and quality. And we'll show some examples of that today. We are experts in wavelength conversion, which allows us to optimize our lasers for both the green and the UV wavelengths. And we have over 130 patents that we have been awarded over the years that have helped us to keep on the forefront of innovation with these different laser technologies. And then, of course, we have a deep expertise in material processing, and we'll share some of those results with you today. And then finally, all of this needs to be brought forth to the customer in value-added type platforms, and we work very hard at keeping our costs down so that we can provide significant value to our customers, not just in the initial purchase of the equipment, the laser equipment, but also in the long-term operating costs. So now let's move on to speaking about our presentation today. There are certainly a number of challenges in manufacturing mobile device displays today, and specifically when we think about the flexible display materials. I think you've all seen either a demonstration or commercial, or maybe you even own one of the new flexible mobile smartphones. But these materials have become quite exotic, and they create some wonderful attributes for the user in terms of flexibility and in terms of color and quality enhancement and so on, but they're also quite significant challenges in terms of processing this material. So there are polymers and hard coat materials that are inherently very flexible and lightweight, but they can be challenging to process. And then ultimately, you can change from a polymer over to a thin glass material, or what we call an ultra-thin glass material, as the surface, the interactive surface for the user, which can be scratch resistant, but also very challenging to manufacture. And this is what we're going to focus on in some of our results today in terms of the application processing. And then finally, we'll wrap up talking about some glass micro-welding techniques that we have developed recently, which can provide some very unique ways of bonding glass together without the use of adhesives, which can be very exciting for a number of different applications in mobile displays and medical devices. The lasers that we're using in our processing today are part of our IceFire industrial picosecond line of lasers. Our IceFire line runs from the infrared, we have a 50-watt infrared model, through 2 models of ultraviolet lasers, both 30 watts and 50 watts, for different types of processing capability. And of course, the added power can improve and enhance speed of processing. And all of these lasers provide unprecedented versatility, which I'll talk about in a moment, with being very compact for industrial picosecond lasers. And of course, they're designed for 24/7 reliability, so that our customers can put these lasers into action and run them for several years uninterrupted with very minimal maintenance. We have been working very hard on enhancing and enabling key applications utilizing some of this flexibility of these lasers, and ultimately trying to bring that applications expertise to our customers, and then in an industry-leading cost performance type platform. So I hope you'll be interested in some of the results that we have today and maybe interested in talking to us about these lasers further. One of the things that sets our IceFire product line apart from other suppliers is the unprecedented versatility in something we call time shift picosecond. What this does is allow us to create a burst pattern waveform, and that burst pattern can be, we can actually adjust in different pulse frequencies to take whatever burst mode it may be and have at whatever frequency we want to specify in the laser. So it could be any variable of different pulse repetition frequencies. Within the burst itself, we can have variable individual subpulses and intensity of the subpulses, and then finally being able to separate those subpulses by the industry's lowest available subpulse separation of 10 nanoseconds, which really makes it quite useful for optimizing the process with the specific material to get either the quality or perhaps the speed enhancement that you may be seeking. Here's a close-up oscilloscope images of some of these kinds of burst patterns, and you can see how we can have the burst highly customizable for various different burst spacing. We can have a 10-pulse burst at any variable repetition rate. We can actually change the intensity within the burst itself to have different intensities of the subpulses, or we can do things such as short as 10 nanoseconds separation within the pulse. And again, being able to vary these different types of subpulses and the different kinds of shapes that you may want to have and the separation between the subpulses allows us to optimize the process for the specific material and the specific outcome that our customers are seeking. So now I'd like to turn it over to my colleague, Jim Bovatsek, to speak more about some of our specific results dealing with mobile devices and glass processing. Jim?
Yes, thank you, Scott. So first I'll talk about a market that's driving a lot of laser sale activity and laser development activity, which is OLED and flat panel displays. What you see on the left is a graphic of a foldable phone, something new on the market, and we expect it to be a very big technology over the years, allowing a lot of usability to be further miniaturized with the ability to fold the screen. And you see a cutaway of a full display, which includes many components, not just the display, but you have on top of the display the polarizer, a touch sensor layer, and even finally the cover window, which is for protective, protects the display itself from scratching and other damage. For the cover window, there are a couple options. Ultra-thin glass, which is thinner is better for achieving a small bending radius of curvature, which allows the device to be more compact. Another technology below the ultra-thin glass there on the right is a polymer with a engineered hard coat layer. This layer is much harder than any polymer, and it is engineered for scratch resistance, but also can be engineered for anti-fingerprint properties and also anti-glare. So that's a brief overview of a simple display, which is actually quite complicated when you look at all the different layers involved. And in the aggregate, presents a lot of manufacturing challenges, which lasers happen to be a big part of. So I'm going to go with a brief overview of light interaction with transparent or non-transparent dielectrics, basically non-metals such as polymers and glasses. If you have a long pulse and a transmissive wavelength, the light simply goes in and comes out. This can be long pulse or even low energy ultra-short pulses. If you shorten the wavelength, you can get absorption at the surface and create ablation feature, material removal, etc. With a longer pulse width, there are tendencies for heat effects. Could be a melt layer. Could be, if it's a brittle material, you could have chipping and micro cracking as well. Now, switching to shorter pulse widths in the pico and femtosecond regime, if you have that same short wavelength, you get the stronger absorption, even stronger absorption with nonlinear effects, and you can get a clean, shallow removal region. And with the right process parameters, you can have a very low heat input and very high quality surface machining. Now, if we go to the transmissive wavelength, because of the very short pulse widths and the high intensities, you can focus that transmissive light and trigger nonlinear absorption phenomena. And this allows you to, at a location of your choosing, based on your focusing, create this absorption and coupling of energy to the material, and then you can get subsurface high quality features as well. So this was really one of the sort of game changers that ultra-short pulse lasers, especially higher energy ultra-short pulse lasers, brought to the material processing world. But sometimes you may want heat. So if you want heat, The way you can do it is take the same ultra-short pulses, but generate them at a very high pulse frequency. In this way, with a dielectric material, you have sufficiently short spacing between pulses so as to create a localized heat area, and this can lead to interesting capabilities with the laser, which we'll see later on in the talk. I'd like to go over the bulk of these results will be infrared picosecond laser, but first I want to touch on some OLED processing we've done with the UV picosecond laser. In this case, our current flagship 50-watt UV laser at 1.25 megahertz, the IceFire 355-50. So on the left, we have a couple polymers, PET, polyethylene terephthalate, and COP, cycloolfin polymer. PET is really a workhorse for OLED displays. It's used in many areas, including the substrate, but also for the touch panel and other areas. And we see a nice, clean cutting result with less than 10 micron heat affected zone. COP is very good for polarization capabilities, and similarly, we show a high quality result. In this case, if you look in that little green box, we see that we were able to reduce a heat affected zone from a 20 microns down to a 10 micron extent, and this came at a very small sacrifice in speed to achieve this 50% reduction. On the right, a few images showing a much more recent result. This is one of those protective cover materials for the foldable phone. This is a polymer plus a hard coat thin film. In this case, the polymer is a clear polyimide. You can see in the right-hand cross-section image. And then the hard coat is about roughly 12 microns or so. And then there's a protective PET cover material. So we have a nice result, very low heat effective zone, very low chipping achieved with our UV laser. So that rounds up some of the UV picosecond processing results for OLED display manufacturing. And let's jump on to the meat of this talk, which is processing thin glasses with welding and cutting capabilities. For cutting glass with picosecond lasers, it's been pretty well established that a bezel beam is a good setup to go with infrared picosecond lasers. The image on the left shows, the graphic on the left shows an Axicon lens used to create a bezel beam out of a Gaussian beam. It's a very long, extended focus with a very short beam radius. And to the right of that graphic, we have another graphic showing really a capability of the bezel beam that allows full depth processing of the glass. You create these blockages, which would be a subsurface microstructure in the glass. And just a short while later, because of the way a bezel beam works with the beam folded onto itself, the light is able to reconstruct and reform a high-intensity region down behind that defect that was created initially. So with that phenomenon, you can create a series of defects throughout the thickness of a glass, which then can be used for breaking along the desired cutting path. And on the right, we have some general basic optics used to generate a shortened bezel beam. Shortened because the initial bezel beam is several millimeters, maybe tens of millimeters long on the left, and then you have a couple of reducing lenses to create a much shorter, much more high-intensity region in the glass, in the workpiece that you're trying to cut. So this is a type of optical setup used for the cutting results that we'll be looking at. Of course, there's other parameters other than the beam intensity distribution, such as the spacing of the pulses in the material and the number of pulses as well. Here we have a sort of a development demonstration for optimizing the spacing of the pulses in the material for creating the highest quality glass cut. So the top row of microscope photos, we see the sidewall cross-section for a pulse pitch going from 4 to 3 and so on down to 1 micron spacing on the material. The spacing is adjusted by changing a combination of either the scanning speed or the pulse repetition rate or both. And then the bottom pictures show the top view where we see the quality going from irregular dots, ablation dots, down to a very fine scribe line. So if you look at the 1 micron pitch, you can see a very nice jump in the quality of the cut that was achieved. And graphically, measuring the roughness, this is shown on the right-hand side of the slide. We have the pitch on the horizontal axis, and from 4 to 3 and 2 microns, you have a linear improvement in quality, which is basically the reduction in the RA, roughness measurement. And then when you go from 2 to 1 microns, we have a jump, basically a doubling of the improvement that we see going from 4 to 2 microns. So this was a very nice result to see, and we demonstrated this quality and actually improved on the 0.2 micron roughness in the next material, which is this is a 100 micron thick ultra thin glass, and the photo at top left shows the surface view before breaking the glass, a very clean continuous scribe as we saw before in the previous slide. And then once you break, the quality is maintained, and once again, very clean quality, no chipping along the edges to speak of, at least at this magnification. And then the sidewall roughness, here we see the 100 microns thickness, and the actual roughness in this case is it was measured less than 100 nanometers, and we tend to see 60 to 80 nanometers sidewall roughness. So very low roughness. When you look at it with the naked eye, it actually has almost a polished appearance to it. With conventional glass cutting, you'll see typically a frosted appearance, but once the roughness goes down below 100 nanometers, it looks quite polished, and we believe that this is something that could reduce in the post-processing time required as far as cleaning up the edges of that glass for the downstream processing, such as actual assembly of the mobile device that it may be used in. So switching up to glass micro-welding, we have various applications. As Scott mentioned a couple. There's medical devices, lab-on-chip, miniature optical assemblies. There are definitely challenges for this type of manufacturing as far as bonding glass with adhesives. You have outgassing, long cure times, automation challenges. There is an adhesive-free option, which is anodic bonding, but this is high heating, high voltage, and a long duration, which could be challenging when you have sensitive components. Lastly, we come to micro-welding, laser micro-welding. We have localized heating. No additional materials are introduced into the process, and there's a lot of flexibility as far as defining contour paths, etc. Our first result to show is glass-to-glass micro-welding. These are 2 glass plates, about 1 millimeter thick, contacted optically, so there's no air gap in between. And we see a top-down microscope view showing a very clearly modified region, which we hope is where the glass is fused together. And the central stronger modification is about 30 microns wide, and we have a larger, more gentle modification of about 80 microns wide. Now, the viewers you may notice this periodic modulation within the central 30 micron region. This is not due to the individual pulses irradiating the material. The pulse spacing is actually much smaller than that frequency you see there. This may be a feedback mechanism where the melting and the plasma causes a defocusing of the beam, and then as the material translates, it refocuses to that optimal tight focus and creates the same identical modification. So some sort of feedback process is likely at work there. Now, is it really welded? We have some cross-section views of several welds viewed face-on, and we do see the interface of the glass, and we see in this case actually 5 fusion welds. And you can see the larger outer region and the stronger central region, And if we blow that up a little bit, we get a little bit better view showing the fine structure, but very clean overall, no chipping or fracturing, etc. So this is a very nice result to see with our picosecond ice-fire laser. So in some cases, spot welding might be a preferred approach for joining, bonding a couple of glass plates. So we did a series of experiments using a variable power and a variable number of pulses. First, let's talk about the variable number of pulses. The data plot on the left shows a very low pulse count, below 1,000, maybe a few hundred pulses. And we increase, this is a logarithmic scale, so we increase quite strongly up to over 100,000 pulses, stationary pulses at 1 watt. We see the growth in the melt diameter, which is the vertical axis. And then as we go beyond 100 or 125,000 pulses, we see some instability in the melt region. So something about the melt pool that's being generated and the stationary beam is creating a little bit of instability. But what we can do is then back it off to where we have a good large melt diameter in a fairly stable regime, which is 125,000 pulses. And from there, we can increase the power. And by increasing the power from 1 watt, you see, to 1.5, all the way up to 2.5 watts, which is still quite low for a 50-watt laser, we have a large increase in the melt diameter, and roughly with every half of watt of power increase, we find a 25 micron increase in the melt spot diameter. So this precision of control is illustrated with the images at the right. We have the very smallest picture with the low pulse count of 16 micron melt width, and then contrast that to the very large melt size of roughly 140 microns, and each spot, whether it's a small spot or a large spot, is very repeatable, very smoothly symmetric about the center of the focus and the center of the energy input into the glass. So that's the basically a wrap up for the glass type of welding experiments, and we also wanted to look at joining glass to metals. In this case, we have glass to aluminum. It's a polished aluminum, but it's not quite a mirror polish. You can still see some striations in the aluminum. And in this case, there's no optical contacting ability, but we did clamp the glass onto the aluminum workpiece. What we did to make a large area that could be inspected was we rastered the beam back and forth, and we rastered about several lines to create this patch of joining, we hope. And if you continue the inspection with the microscope, you see the series of lines spaced by roughly 30 or 40 microns. And with the dark field microscopy, you can see a little bit of, dark field is very sensitive to any surface irregularity. And at the edge of each dark scribe, we see a little bit of scattered white light and maybe a little bit in the middle of the laser process line. But overall, nothing very extreme in terms of strong ablation or strong molten aluminum or glass chipping and whatnot. And we were able to also create some cross-section views. So this is an edge-on view. The glass material is at the top, and the aluminum is at the bottom, sort of a yellow-orange color at the bottom. And what we see is these very fine pyramid structures of aluminum protruding into the glass. So we see no delamination between the glass and the aluminum. And this joining was demonstrated by the fact that it was joined. We don't have strength test results, but we could break the glass off, and in breaking the glass off, the very large chunks of the glass remain bonded to the aluminum. So we're confident that there's quite a good welding achieved there. And that concludes the glass welding and cutting segment of the slides. Can summarize advances in processing mobile displays. We have a wide range of materials in the displays. Ultra-thin glass can provide good durability for foldable displays. Using ultra-short pulse lasers, we can cut ultra-thin glass with very high speed and very good cut quality. The glass micro-welding offers advantages over non-adhesive bonding, glass to glass or glass to metals. And lastly, the ice fire laser, whether it's a picosecond IR or picosecond UV, operates in a wide range of conditions for a variety of applications for mobile devices. We have burst mode, which was used in ultra-thin glass cutting, and the very high repetition rates of up to 10 megahertz were used in the glass micro-welding. And that concludes this section of our talk, so thank you very much for your attention there.
Yeah. Thank you, Jim. Let's turn it over now to John McCauley, our colleague from Ophir, to talk more about some of the control and process equipment. John?
Thank you, John. I appreciate it. As always, I want to thank Laser Focus World for the platform to speak. It's been always a pleasure to work with John and Shannon and everybody on the team to provide the platform to speak to everybody. Also want to thank John and Jim for their presentation. I actually got my start in laser applications, so presentations like that always interest me, and I know Spectra-Physics has an incredible product line, and so thank you for that presentation. Let's shift gears a little bit and talk more specifically about the control equipment that Scott and Jim mentioned briefly in their presentation. I want to talk about measuring industrial lasers. That's primarily what I'm working with these days, are high-powered industrial lasers used for these welding, these joining, these cutting applications. But I want to address some myths that have arisen over the years, specifically about industrial lasers and also about the measurement of these industrial lasers. So just to talk about an overview of my presentation, I just want to start off by saying the application of lasers for material processing is becoming more and more commonplace in industry. I think that people who are working in laser applications are doing an incredible job on their research, finding more and more applications of the laser to replace traditional processes. And we're just seeing lasers being used more and more in industry, which is an incredible time and an exciting time to be alive. As industrial processes advance, so does laser technology. So so not only the laser light itself and the way that the laser light is generated, not only is that technology advancing, but the systems in which the laser light is encompassed around and enclosed around, those technologies are advancing as well. Industrial technologies in general are just advancing to a point where machines are becoming smarter. For instance, you've got the age of the Internet of Things. You've got Industry 4.0 that are allowing laser users and just everybody in industry to work smarter at their processes. And so as those advancements take place, so do advancements in laser technology. But even though, we have these advancements in technology, there's still a lot of myths that surround not only the application and the employment of lasers, but also the operation and maintenance of lasers. Depending on where you are in the laser life cycle, there are still a lot of myths, and I kind of want to focus my presentation on these myths. There are myths around how light behaves in material processing. There are myths on how modern lasers differ from legacy products, so some of the newer laser systems and how they're generated, how they're integrated, how they're applied. Those differ from lasers of the past, but still some mindsets and some some myths have carried over from, the use of legacy products. And also when and where measuring laser performance is important and critical. There are a lot of myths surrounding that as well, so I'd like to address those as well. And, just to make a general statement here, separating fact from fiction is really vital to ensuring a long-term, high-quality laser process. When we talk about material processing lasers, there are some things that have changed and there's some things that have remained the same. So what has changed with material processing? Material advancements. We saw in the previous presentation how we're welding glass to aluminum. I'm still trying to wrap my head around how exactly that happens, but that's just, in my mind, that's just amazing that we're able to get to the point where we're able to join glass to a metal. There's plastics to metal. There's dissimilar metals that are being joined and even cut. So there's advancements in material. There are more stable sources. I know that Spectra-Physics, they make an incredibly stable source, and they put a lot of hard work into achieving those types of stable sources. And just everybody is really doing a really good job with respect to that. Creative engineering of work cells. So system integrators, when they take a laser source, they enclose a work cell around it. We've got smarter work cells. We've got just better working, more efficient work cells, and there's a lot of creativity that goes into that. In addition to smarter production environments, like I mentioned earlier, we're just getting to the point where we need this feedback about the process in order to continuously improve it, and in order to make it just an overall smarter process. But with things that have changed, there's also things that remain the same. The application of lasers, the limits are being pushed. I'm sure that Jim could talk about how he takes a laser and he sees how far he can push that laser. How fast can we get that laser process to happen, or how much power can we actually get out of the laser? The application of the laser is being pushed. That's always gone on. Lasers and laser systems are still made of physical matter. So regardless of how you're generating the light, regardless of what kind of system you're integrating that light source into, and no matter how you apply that laser, it doesn't change the fact that lasers are still made up of physical properties and or physical components, and then susceptible to physical properties. A lot of these industrial lasers are put into very harsh production environments. That has not changed. System integrators are doing an incredible job at taking a laser source, trying their best to remove that debris from the process in what would otherwise be a very dirty environment. But there are still some harsh production environments there that will affect the laser performance over time. Just a general statement, laser systems will naturally decrease in efficiency over time. That's just because of these harsh environments. It's just because these laser systems are susceptible to physical properties because they're in the real physical world. So I just want to talk briefly about what power density is. Power density is really the general definition of how the laser interfaces or interacts with the material that is doing the processing. It's just a real simple concept to understand. Power density is it's broadly defined as the measure of how the laser is being applied to the material that is being processed. Power density must be maintained regardless of the laser application. So you may have a pointing laser that you bought from CVS, or you have a high energy defense laser that you use for shooting down drones. It really doesn't matter. If the power density is lost, regardless of how the laser is used, that laser in effect will eventually become useless. So maintaining the power density is really vital to ensuring that you do have a stable laser process over time. The concept of power density is expressed in this formula here. It's watts per centimeter squared, where the top of the formula is the W. It's effectively the amount of laser light that's being applied. And then the bottom of the formula is this centimeter squared. That represents the beam size that the laser light is focused down to. So you have a quantity of light, and then you focus it down to a beam size. Both of these laser parameters will define how the laser is interfacing with the material that's being processed. The bottom of the formula, it's also known as the beam size, the spot size, the focus spot. There are a lot of different names for it, but it's the amount, it's the size of the light that is being applied to the process. So how do each of these parameters, both the amount of light and the focus spot size, how do they change when the laser process material, when the laser processes material? Well, if you have, for instance, I just got a couple examples here. One, if you have a degrading component within your laser system, so you have an aging optic, something that's absorbing some light, it's going to decrease the power over time. It may be a gradual decrease, but it is going to decrease the power over time. What's that do to the power density? It affects the top of the equation, which decreases, so the overall power density is going to decrease. The second example is, say that you have some kind of a thermal effect on your multi-kilowatt laser system that's causing the location of the focus spot to change. Well, what's going to happen? The focus spot at the material is going to increase as you have a shift in the focus spot. Well, what's it going to do? It's going to increase the bottom of the formula, which is going to overall decrease the power density. Again, if you're using it for like a welding or some kind of joining application, we have a decrease in power density. You're going to lose the weld, and that's how your power density is going to affect the process. So let's look at some of these myths. I've got 3 myths that I want to talk about. This first myth is very common. It's one, as we in laser measurement hear quite frequently. When our laser is new and very stable, measuring the laser performance isn't that necessary. And to a degree, I'm going to agree with this product. When you do have a new system that's been run in, it's been measured by your integrator, you got your factory acceptance test, yeah, you are going to have hopefully a very stable laser process for some given amount of time. So no matter how the laser is used, the success of a laser process depends on a consistently forming laser. So you have a new process, yeah, you might have a very stable laser, but there is going to come some point in time, it may not be the near future, it may be several years, but you are going to reach a point where that laser process is no longer performing the way it was designed to. So this really comes down to is a question of when should a laser be measured, which is another question that we get all the time. Ensuring a laser performance is really crucial throughout a laser's life. So not only is it crucial to measure at that system runoff, right, when you have a new laser, but there are also some other times during a laser's life where it is very crucial to understand how the laser is behaving. So you have a baby laser here, you have a source that a source manufacturer is developing. I can speak with Scott and Jim, and they are probably extremely interested in verifying not only that they have the spot size that is designed to work with that application, not only do they have the power level that power energy level that they are expecting for that application, but they're also very interested in laser quality parameters like M squared, beam parameter product, Rayleigh length, those type of measurements. So when you're developing a source, those measurements are extremely interesting. You have your teenage laser here. That's where you're taking that laser, you're starting to apply the laser in different applications. You're starting to see what all that laser can do. Measuring a laser in an application or a research phase is extremely important because ultimately the entire process that laser is going to be used for is ultimately going to have to come back to that original application. And so capturing the laser data at that application phase of your laser is extremely important so that you have those benchmark measurements and you can ultimately come back to that. We have a middle-aged laser here. The laser, the application is developed. That laser is taken and integrated into a system. This is also an extremely important time to capture that laser data, because ultimately when your laser process starts to fall apart, you want to come back to that original not only application, but when that laser was integrated into the system, you want to come back to those benchmark measurements. And then you've got your laser in your later stages of life. Just like a lot of us are, we require a little more maintenance, a little more medication, a little more attention to our health. A laser is no different. So you commission a laser and you put it into production. Eventually, it's going to start to degrade, like we've talked about before. So being able to take those previous data points and restore that laser to its designed function, its designed process is really vital. So measuring, my point is that measuring a laser over its entire life cycle is really important if you do want to protect your investment. Only through laser performance characteristic measurement and trend analysis can a laser user know for sure that the process is stable. I think I've made that point. Myth number 2. So we hear this a lot, especially when talking about industrial lasers. And specifically talking about kind of legacy systems, but the same can still be said today. So we hear a lot, when the process starts to drift, we just turn up the power and we keep going, right? So what's the issue with this mindset? There are really a couple of issues. Just to kind of explain what's going on here, I like Scott's slide that he showed earlier. His is a little more sophisticated than my slide, and I might steal that from him for future presentations, but mine's a little more rudimentary than his was. But, a laser system, it starts off with a source, and, regardless of how you're generating that light, maybe a fiber or direct diode, disc laser, CO2, you send it through some kind of delivery system, free space optics or bellows, maybe a process fiber. It goes through shutters, apertures, purge gas, and then eventually it reaches some kind of processing head. It's got some beam shaping optics, some mirrors, some lenses, a cover glass, some other parameters that might be on that processing head. My point is that laser is going through stuff, and more stuff, right? So it's touching all of these things. So where you might start off with, and these are very real beam profiles that I've collected over the years, you might start off with a nice Gaussian, beautiful beam like that, but once it touches a mirror that has been misaligned or something along, like a speck in the middle of the mirror here, your laser process might start to degrade because of that fact. And then by the time it reaches your process, that focused laser looks very, very different from the laser that started off with. So measuring, understanding, and knowing when to take maintenance actions on your laser are very, very crucial to a stable process. There are many, many reasons why a laser wouldn't operate as designed, regardless of how the laser is used. I've got some pictures that I've taken here over the years of some things. Faulty manufacturing. We see a misaligned cutting nozzle. Just the operator was a little uncareful about how he put that nozzle on. A faulty component that can happen pretty easily. Improper maintenance is something that I've seen out in the field recently that caused a real big problem. An improper maintenance practice that was in place. Environmental factors. So, I mentioned that, some of these industrial lasers, they operate in very harsh industrial environments. There's a lot of process debris. Those can obviously have a very negative impact on the performance of your laser. Contaminated cooling water, purge gas, really a lot of things that could happen to your laser system that could cause the system to decrease in efficiency. As long as laser systems are susceptible to human error and physical limitations, the performance of the laser will change, or at least it has the potential of changing over time. And, it's usually not for the better. I've never known a system to degrade and then cause the overall efficiency of the laser to increase. Let's just say it that way. and we get back to our original myth that when the process starts to drift, we turn up the laser and keep going. Really, if you want to be honest about this, what are we doing here? We're trying to get parts out the door without really addressing what the problem is. And as long as lasers are, susceptible to these degradations because of the physical limitations, your costs of manufacturing increase ultimately, and ultimately you run the risk of looking at a very, very large maintenance bill when you don't address the problem to begin with. Changing process parameters and avoiding the problem of process drift is kind of what I named it, is really not an effective solution, and it really can be a very costly decision for you to neglect those types of changes. Myth number 3, this is one that we hear quite a bit, and I want to address this myth because we are talking about equipment that measures your laser performance. Myth number 3, measuring laser performance is way too costly, it's complicated, it's time consuming. I'm sure that any of you who have been exposed to laser measurement systems in the past have really kind of walked away from that experience with maybe this kind of mindset. And so I want to address this myth before we wrap this up. Historically, laser measurement, it has been expensive. It has been pretty complicated to use. It has been, relatively unstable in its performance, and it has been kind of delicate, right? So Ophir, we've done an extremely good job on selling instrumentation into lab environments, research environments, and so those types of laser users are really used to using our equipment, and they value that the information that these products will provide them. However, you put those into an industrial environment, with an industrial mindset, with a, John, I've got to get parts out the door, I'm not really that interested in this kind of, mentality. And, I can see where the measuring laser performance is too costly, complicated in time, because I really can sympathize with that mindset. However, today, laser measurement is really of higher value. I hesitate to say that it is less expensive because it's and oftentimes it's not expensive. Ophir really is the best equipment that you can buy, but it does come with a cost, and the return on investment is much higher these days than it has been in the past. They are much easier to operate. I've got some products here that are shown, these all-in-one components, component called the Beam Check, the Beam Watch AM, specifically engineered for additive manufacturing equipment, and then the Beam Watch Integrated, which is an all-in-one integratable product into a laser work cell to measure multi-kilowatt lasers. All these products are extremely easy to use, extremely easy to interface with. They are better for performing than they have been in the past, just due to cameras which have higher resolutions, faster data rates, etc. And they are more robust in design and really intended for industrial use more than they have been in the past. So just to wrap up my presentation, I'll just make a few statements and then I'll turn it back over to John. Laser technologies continue to advance and provide more stable processing, but laser systems will always be made of physical matter, and this will always result in changes in the laser system. New laser systems are usually stable, I'll admit that, but changes will happen in time. And benchmark laser performance measurement, they really do help return a process to its intended state. And when you think about the investment that you make in laser measurement equipment, it really does provide a very strong return on investment when you look at how you're able to prolong the life of the laser and its process. When the process starts to degrade, a comparison of laser measurement can be used to restore the process to its intended design. And then finally, while historically laser measurement solutions have been limited in their value with the information that they supply, today's products provide the laser user with solutions which are much more comprehensive in their analysis, much more durable in harsh environments, and give a higher rate of return on your investment. So that concludes my presentation. And John, if you want to take it back, we'll answer some questions.
Thank you, gentlemen, for that very interesting presentation. I really appreciate it. Now we have just a few minutes left to answer some questions. So once again, I'd like to invite our audience to use the Ask a Question box in the presentation windows to submit your questions to this panel of experts. So I guess we'll start with, for Scott and Jim, whichever one you think is best suited to answer this question. What is the relationship between burst pulse separation and pulse spatial pitch?
Jim, I think I'll let you address that one.
I'm sorry. Can you repeat the question? I'm sorry. I was trying to find the question window.
Oh, no worries. The relationship. What is the relationship between burst pulse separation and pulse spatial pitch?
Okay, so the burst pulse separations are very short. We have the industry leading 10 nanosecond, and in truth, a lot of processes benefit with the very short burst spacing. When you're talking the spacing on the material, the time scales are much longer. So when you see these individual surface dots from the laser output on the material, that's actually the aggregate of many pulses in the burst. For the glass cutting, it's typically 2 to 4 pulses with that short 10 nanosecond spacing. But really, when you're scanning at hundreds of millimeters per second, that is actually all, those pulses are encompassed within the single spot on the material.
Thanks, Jim. This one looks like it's for John. What is the difference between power density and irradiance?
Power density and irradiance. So I'll just say generally nothing. I mean, it's effectively the same concept. It's how much light and versus the size of the light. So power density is really used specifically for lasers, and when you have a laser that's doing some kind of processing. But irradiance is a measure of flux energy in kind of lighting applications. So you see it more like maybe with medical lasers or some kind of automotive lighting, relatively lower power, but ultimately it's the same concept. It's how much light you have versus the area at which the light is shining on, but effectively the same thing. It's a good question.
Thanks, John. Next, for Scott or Jim, what is the maximum glass workpiece thickness you can handle?
Okay, this is Jim. Yeah, that's a good question. With the glass, I'll speak to the welding. As far as handling, that depends on the mechanics and material handling of the surround the workpiece, things like that. But for the welding, we're really concerned with the thickness because you're focusing through the glass. It's a through transmission welding, and you need a tight focus to avoid cracking and large-scale heat effects. So with the optics we use, the working distance of the A-sphere, Newport A-sphere lens objective is about 6 millimeters. So I believe we should be able to handle thicknesses somewhere around 4 or 5 millimeters, but we haven't tested that yet.
Thanks a lot, Jim. Unfortunately, we were not able to get to all the questions today. However, we will certainly forward them on to our panel of experts and have them so that they can respond to you offline after the event. I'd just like to ask our guest presenters if they have any closing remarks for the day.
I'd just like to say, John, thank you again to Laser Focus World for hosting this, and we appreciate the opportunity to bring some of our technology out to prospective interested folks in the industry, and we certainly welcome your feedback and continued dialogue.
Oh, thank you very much. Before we sign off, I'd like to thank today's speakers once again, Scott White and Jim Bovatsek of MKS Spectrophysics and John McCauley of Ophir for today's presentation entitled Materials Processing, Lasers, Optics, and Testing. I'd also like to thank today's sponsors, MKS Ophir and MKS Spectrophysics. I would like to remind our audience that the webcast on-demand version will be available on the Industrial Laser Solutions website, and the link to the archived webcast will be sent to you via email within the next 24 hours. On behalf of Industrial Laser Solutions and Endeavor Business Media, we thank you for joining us today and look forward to serving you with future webcasts.